All right, so lecture number 21, microstructure analysis techniques. So I think this week we're going to talk about techniques for microstructure analysis of concrete and other materials. We are going to talk about scanning electron microscope, SEM, XRD, okay, which is X-ray diffraction method, MIP, which is mercury intrusion, porosimetry, among other methods. Okay. Today, I think we're going to talk about XRD and also MIP if we got time. Okay. How to measure cement compound composition? Okay. One of the methods we discussed before is we call image analysis method, which we take a picture of a cross section of cement clinker, okay, and based on the color and also the shape of different components. For example, this is a cross section of cement clinker. If you remember, the light color, crystal, angular shape, it is C3S, okay, and the dark circular color, it is C2S, okay, and the phases in between, we call that liquid phase. So liquid phase is a mixture of C3A and C4F. Okay, so let's see if we take a picture of cross section, and we want to know the volume percentage of different phases, different compound. Okay, we can count the areas of different phases in these pictures by counting how much pistons, number of pistons for each phases. Okay, and we can assume the number of pistons will be, the ratio of number of pistons will be similar to the areas ratio, which in turn will be similar to volume ratio. So based on that, we can estimate the percentage of different compounds. Okay, so I think we discussed this method in lecture number 3 or 4 when we discussed the cement chemistry. Right. X-ray diffraction is another technique we can use to tell the percentage of different compound, or at least what are the compounds inside a certain sample. Okay. So let's consider we have a perfect crystals with atoms arranged in a certain ordered manners. So if that phase are crystals, okay, then the distance between certain atoms will be fixed for a certain type of materials. Okay, for example, the distance between these two atoms will be fixed. Okay. All right. So before we talk about how to use X-ray to check the phases, let's talk about a composition of different waves. Okay. Let's say we have two waves, wave 1 and wave 2. So this is one period. Okay. So and this is another period. Okay. So if wave 1, wave 2 are in phase, okay, like in this case, starting from 0 in distance, they have 0 in amplitude. Okay, and then they both wave 1, wave 2 increase over the distance, and here they are all at the crest. Okay, so we call wave 1, wave 2 are in phase. So the amplitude can be added together. So the net amplitude will be 2A, so which is amplitude for wave A, wave 1 plus amplitude for wave 2. Okay. So again, we call that in phase. In this case, V1, V2 are out of phase. As we can see at distance 0, V1 has 0. Okay, but for V2, it is already somewhere here. It's not in 0. Okay, and when V1 at crest, V2 already passed its crest. Okay, so in that case, we call that out of phase. Out of phase. Complete out of phase when V1 and V2 is like this. Okay, so this is V1, this is V2. Okay, so for example, when V1 is 0, V2 is at its crest. Okay, and then at here, no, sorry, it should be here, somewhere here. So at some time, the V1 and V2 can offset each other. Okay, so amplitude in somewhere could become 0. Okay, so we call that complete out of phase. Let's say we have one crystals and the distance between certain atoms is fixed. Okay, distance d. Let's say we have V1 here and V2 there. All right. So V1 will meet these atoms and be reflected back. Okay, and the angle of the wave is called angle of incident. Okay, and look at wave 2. Wave 2 also have angle of incident of theta. Okay, but it reflected from this atom and reflect back. Okay, look at the difference in of travel. So travel distance between wave 1 and wave 2. Okay, so wave 2 traveled longer than wave 1. How much longer? It is this march, okay, plus this march. Okay, and this is 90 degree. All right, so this is rectangular angle, triangle. This side is D. All right, so because theta is here, this is theta. So this angle is also theta. Okay, so based on that, this side will equal to D sine theta, right? So, and this side is also equal to D sine theta. So the total distance wave 2 traveled is 2D sine theta longer than wave 1. Okay, and in this position, if 2D sine theta is equal to n lambda, lambda is the wavelength of the wave, and n is any integer. So if this happens, these two waves, we said that in phase, because amplitude will be added together. So the intensity will be higher. Okay. If this equation does not satisfy, because it is depending on the value of d and also the theta. Okay, for certain rays, for example, X-ray, lambda is fixed. Okay, so when we change the theta and d, we have different peaks. Okay, so when this happens, we call that is verified when waves are in phase. Okay. And again, the d value is fixed for a certain type of crystals, and lambda is also fixed for a given X-ray. When we change in the theta at certain angles, we will have in phase of the waves. And if that happens, we're going to see higher intensity. So we call that Bragg's law. Okay. So in X-ray diffraction, we change the theta, and then we measure the intensity of the response. Okay. When Bragg's law is verified, 2D sine theta is equal to n lambda, then the intensity of the X-ray will be higher. Okay. And based on that, we can have something. Okay, this is I is for intensity, XL is theta. Okay, so we're gonna see some thing like this. Okay, at a certain theta, we see intensity. Okay, and relative height of intensity, the peaks will be constant for certain materials. Okay, so it's like a fingerprint for certain type of materials. Okay, and based on shape of the curve of I versus 2 theta, we can identify what are phases in a certain sample. Okay. Here shows example of planes in a cubic system. Okay, planes could be between B, E, and G. This is right angle, or A, E, G, C is another plane. Okay, or ECGF is another plane. Okay, so for certain crystal materials, we have several planes, which is fixed with a fixed distance. To use X-ray diffraction method, we could use either the Lowy method or the powder method. The powder method is by far the most commonly used method. But let's look at the Lowy method first. We use X-ray directly on crystalline materials, but this is not powder form. Okay, like we did in the powder method. We get the sample, we cut the sample, and then we use white radiation. Okay, for white radiation, the lambda will be variable. Okay, there's more than one wavelength. Okay, for white radiation, but the incident angle theta is fixed. Okay, for powder method, we first grind the samples into fine powder form. Okay, so typically less than 80 micrometer. Okay, so crystal is reduced to powder form, and then the lambda is fixed. We only use one light, such as X-ray, certain type of X-ray, so the lambda is fixed, and we change incident angle by rotating either the sample or we rotate the source of the X-ray. So the theta is variable, and then we monitor how the intensity change over theta. Okay. Right. This is Lowy method. Again, lambda is variable for white radiation, but we do not grinding the sample into powder form. Okay, and the rays are diffracted. Okay, when it met the atoms. Okay. The powder method is used more commonly. Again, the solid is reduced to fine powders. Okay, typically the grain size is less than 80 micron, so 80 micrometer. The orientation of a given crystalline plane is random. Why that happen? It is because when we grinding the sample into fine powder, so look at the grains. Okay, even though the orientation of a certain plane is random, but for any orientation, we have enough number of particles because we just have so many powders, the particles is large enough. So for any orientation of plane, we have enough particles. Okay. So again, Given the great number of grains, some will be properly oriented to deflect along a certain plane, such as this. All right. So we have so many particles, okay, and the lambda is fixed. We only have one source of X-ray, okay? And each of these cells, each of these particles belongs to a different grains, okay? And each orientation exists for great number of occurrence because we just have so many fine powders, so many particles, okay? And the powder is placed in rotating sample holders. The sample holders is just like glass holders, okay? So we put the powders here, okay? And the powder is placed in rotating sample holders, okay? So in this case, the X-ray is not moving, so the sample is moved. For some XRD machines, the sample is fixed, it's not moving, but we rotate the X-ray source, okay? So when the rotation angles verify the Bragg's law, okay, which is when 2D sine theta is equal to n lambda, okay, when n is the integer, we call that verified Bragg's law. The intensity will be higher. Okay, the maximum intensity of deflected rays is reached. Okay, that's why we see different peaks at different angles. Okay, so here is the example of this is the slag sample. Okay, in that sample, we have more than one crystals, okay, such as magnetite, and I cannot see there. But in one sample, there could be more than one crystal materials. So sometimes the peaks will be overlapped, which make identify different phases, different compound in the sample very difficult. So most likely we're gonna need a software and computer to help us identify the different phases. Okay, but the typical example of powder X-ray diagram will be something like this. The y-axis is the intensity. Okay, the x-axis is 2 theta. It's 2 theta. It's not 1 theta, but 2 theta. Okay. Right. For XRD, we could either do qualitative analysis, which means we only tell what kind of phases, what kind of compound are in that sample. Okay. Or we could do a qualitative analysis. So not only what type, but also what are the relative percentage for each compound. Okay. Let's look at the qualitative analysis first. For that, the goal is to determine the nature of crystalline component. For XRD, only crystalline component can be identified. For glassy phase, it is very difficult because for glassy component, the distance between atoms are not fixed. Okay. So the method is to determine the spacing, the d value, okay, for each peak, okay, and also consider the relative intensity, okay, because the height of the peaks are different. Okay, for example, theta 1 and theta 2, we have two peaks here, but the height of the two peaks are different. We call that relative intensities. Okay, so based on that, we try to match known component. Okay, we can use database from a certain software, and based on the software, it can tell us what type of component are in that sample. Okay, it could be very cumbersome. Okay, when we have more than one component, because the intensities, the peaks, may be overlap for different component. So software is useful. So actually, software is a must to be able to use XRD. So here is an example. Database is necessary. So here shows the D value and also the ratio of intensity, I over I max. In this case, I max over occurs at D of 3.335, and N is the animals. Okay, so this is the fingerprint for CalSat, which is CA03. Right. So this is recorded in specific condition with pure samples of specific region. So there may be different type of CalSat, for example, and then this value may be different somehow. So for qualitative analysis, we can check on a phase of material set by comparing two or more peaks based on the tables. Okay. The analysis may be difficult and time-consuming if software is not used. Okay, and we should better know what we are looking for. Okay, so without that, it could be hard because there's just so many possible components. If we know what are looking for, it will make things easier. It is not very successful with 9 crystal materials. Okay, so this is important. Again, for glassy materials, the D value is not fixed, it's changing. So we cannot tell non-crystal materials using XRD. The benefit is the method is accurate. We can quickly identify what type of phase in the sample. Okay. So crystalline materials can come out quickly, such as ethylene and calcium hydroxide in cement compound. For example, C38 and C4AF. So these phases are glassy phase. It's not very easy to tell. And also for C3S and C2S. But for well-defined crystal materials such as ethylene and calcium hydroxide, XRD is very, very useful. So a sample problem view looks like give us a white color fine powders and give us the XRD diagram with 2 theta angles and also give us lambda. The lambda is fixed depending on the type of X-ray and also give us the database. Okay, so the software can identify the phases in the sample. So the second type of XRD is called quantitative. Not only what type of phase, but also trying to figure out what are the percentage of for different phase. Okay, so in this method, we add a known constituent. We also call that a reference materials. Okay, which has known chemical composition and also known weight. Okay, and then we measure the intensity. So let's see for the reference materials, we have a known intensity I0 and also a known weight fraction. Okay, so I0 and W0 is known, and also the intensity for the unknown materials can also be measured. Okay, so what we want to know is we want to know the weight percentage for the unknown materials. Okay. So if we change the reference amount, so we can accurately control how much reference material we use. So we change W0, okay, then the ratio of W1 to W0 will also change. Okay. So for a certain type of materials, if we figure out what are the unknown materials, and we can plot something like this. This is relative intensity of the unknown materials and the reference materials. What we want to know is W1, okay? And W0 is the weight of the reference material, which is also known. The slope is also known depending on the type of materials. So based on that, we can figure out W1, which is the weight of the unknown materials. Okay. So this is the basic idea of quantitative analysis using XRD. It is not very easy. It's very hard depending on the skill level of technician, but it could be done in some cases. All right, so that is XRD method. The next method we're going to discuss today is called thermal gravimetry analysis. Okay, so this method, the idea is very simple. We just get a sample and we record the weight loss of the sample when we slowly increase the temperature of the sample. Okay, so we monitor change of the weight versus the temperature. Okay, we can use this method to get, for example, how much chemically combined water in a hydrated cement, or even the degree of hydration. Okay. We can also get idea of the quantity of different type of hydrates, but we should know the decomposition temperature for different type of materials. For example, portlandite, we know at certain temperature, portlandite will decompose. If the weight change at the temperature of portlandite, we can get the idea the weight percentage of that materials. Okay. So a typical curve of thermal gravimetry analysis is something like this. Okay. Again, we monitor the weight loss of the materials versus the temperature. So let's see if at this temperature range, we know this is decomposition temperature for calcium hydroxide. And if we know the weight loss of the sample is this much for this temperature, this is gonna be the weight of the calcium hydroxide based on thermal gravimetry analysis. So the idea, as you can see, is very simple. Okay, it's very simple. All right, the next method is gonna be mercury intrusion porosimetry, but we will not finish this by today. We're gonna save it for next time. But today we just give you a short introduction of what is mercury intrusion porosimetry. Okay, so we can use this method to give estimation of porosity of the materials. Okay, so porosity and even pore size distribution, the size of the pores versus the percentage of different size of pores. So we call that pore size distribution. And even the surface areas of the samples. Okay. The diameter of the pores can be checked between 360 micrometer to, this is 0.0055 micrometer. This is 0.55 nanometer. Okay, so the pore size range is very large. So we can use MIP to measure the pore size in this range. Okay. So in porosimetry, we apply a slowly increased pressure. Okay, we force the mercury into the sample. So the pressure range from 0 to 33,000 psi, or around 230 megapascal. So we force the mercury into the pores of the sample at different pressure. Okay. So that's a correlation between pressure and pore size. Okay. So we're gonna talk about that in details next time. but we have a correlation between the pore size and pressure. And when we measure the relationship between the pore pressure and the volume of the mercury pushed inside the sample. So the volume of the mercury pushed inside the sample is the volume of the pores. Okay, so pore volume. So we get an idea of the pressure versus the pore volume, and because the pressure has a correlation with the pore size, so we can have a curve of pore volume and pore size, and we call that pore size distribution. Okay, so let's stop here today. We're gonna continue MIP for next time. Okay. Any questions, Sonny, Derek?